Good morning also from my side. I have the pleasure to chair the first session of our meeting that is dedicated to hydrogen on Earth and exoplanets. And our first speaker on this issue will be Marta Pamato from Padua University. She received her PhD degree in 2014 in experimental geosciences at the Bayerisches Geo-Institut in Bayreuth, where she has been working on the behavior of minerals under extreme pressure and temperature conditions of the deep Earth. She spent some time as postdoc in universities of Illinois and the University College in London before she returned with a Marie Curie Fellowship to Padua, where she currently is associate professor. She has received several awards, among others, just last year, the Research Excellence Award of the European Mineralogical Society, and she's running an ERC starting grant on diamonds as the key to unravel the origin of Earth's water, which aims to determine the Earth's primordial hydrogen properties. So we are looking forward to your talk, Marta, on hydrogen in the deep Earth.
Yes, thank you. Good morning, everyone. Thanks a lot for the nice introduction and invitation. It's an honor for me to be here and talk at the Leopoldina. I've known this academy since I was a student in Bayreuth, and it's really a pleasure for me to be here. So today I'm going to talk about hydrogen in the deep Earth. I'm going to tell you why it is important that we understand hydrogen in the deep Earth, and towards the end, I'm going to talk and explain how we can use hydrogen in diamonds to try to unravel the origin of Earth's water, which is part of my ERC starting grant. Before we do that, it's important, we might have heard that last night, why do we care about hydrogen in general? Well, hydrogen is the most abundant element in the universe, and together with oxygen, which ranks third, they combine and they make water. The presence of water on Earth's surface, and particularly in its liquid form, makes our planet special and unique among the other planets in the solar system. We have here our Earth, which is covered by oceans. And 70% of our Earth's surface is covered by ocean. And this is what makes our Earth planet unique in the terrestrial systems. Water is an essential ingredient for life. It controls many biological processes, geological processes. I'm a geologist, of course, I care about the geology. And it affects many things that we have on our Earth's surface. So it controls life on Earth. Without the presence of liquid water on Earth, we wouldn't have life as we know it. So hydrogen combines with oxygen and forms water. I'm going to exchange a lot these two terms. We do that in geology. And what is important, okay, you say, we know that we have water on the Earth's surface. It seems obvious, but we still don't know how to answer an important question. Where does this Earth water come from? And this is what I'm trying to do with my ERC starting grant. And I'm going to leave this question towards the end. But before we answer this question, we need to ask ourselves two important and fundamental questions. Are the oceans that we see the whole water budget that we have on our planet? Well, the answer to that, I'm going to tell you, is no. We know that we have hydrogen reservoirs deep in the Earth, equivalent to several masses of the oceans. We know that from experiments, from natural samples, and the question is, the second important question, does that matter if we have hydrogen in the deep interior? Well, from a geological point of view, that matters a lot, because if we have even tiny amounts of hydrogen as traces, as defects in the structure of the mineral that form our mantle, that's have a huge effect on geology, mantle processes, differentiation, the evolution, the dynamics of our planet. And understanding hydrogen in the deep earth might help us answer the first question: where does earth water come from? So the answer to that is yes. So we are all familiar with the Earth's water cycle, which affects weathering, sedimentation, geological processes, biological processes on the Earth's surfaces. We have evaporation, the formation of clouds, condensation, precipitation. So we have this exchange between the oceans and the lands. But our Earth is an active planet. We have plate tectonics. We have these parts, the lithosphere, that behave, it looks like a puzzle. We have different plates that move around. And we have the manifestation seen here, this nice image from Mary Tharp, where we have the ocean floors. And you see that we have places like here, the mid-ocean ridges, where we have formation of new crust. And we have other places like Andes, Himalayas, where the plates collide one to each other. So this is exemplified here. We have mid-ocean ridges where we have the formation of new crust, volcanism. These are the so-called spreading centers. The material gets colder, denser, and it then meets other plates, and we can have subduction, the collision of one another. Material gets dragged down to the mantle and recycled. On this way, we might have the formation of hydrous phases, serpentinization, because there is interaction of ocean floor water with the mantle minerals. And that water, in forms of hydrous phases, can be dragged down. And from experiments, we know we can reach even the core mantle boundary, very, very deep in the Earth's interior. Most of them will be not stable. They will dehydrate. They will release fluids, and this will trigger volcanism, okay, that we see in the arc magmas. So we have an input of hydrogen, of water into the mantle through subduction, and an output to the mantle by a volcanism. And this is what we know as the deep Earth cycle. So water, what I'm talking about from now on, is hydrogen that is present in the deep Earth interior, combining with oxygen, making nice bonds, okay? The ingredients of water, if you wish. So the presence even of tiny amounts of this hydrogen can have huge influences in the geology and the evolution of our planet. I'm not going to go into detail. It's not a geology lecture, but what you can see, two examples. If you have amount, here the numbers are ppm of water in the rock. This is depth. You go deeper in the mantle. This is the viscosity, one of the properties that we are after. It affects also how the mantle deforms. If you add water, it dramatically changes the behavior. It lowers the viscosity. And what is more remarkable is it acts to depress the melting temperature of our rocks, of a peridotite, for example. Pressure again, so deep into the mantle, high temperatures. If you have a dry rock, it will intersect the geotherm over here, but if you add water, even tiny amount, 200 ppm, it decreases. It lowers the melting temperature by several degrees, hundreds of degrees. That means that we form melts at great depths. This for us is really important, and this helps to differentiate, chemical differentiation and so on. So for us, it's a big deal. It's really important that we understand hydrogen in the deep Earth. Before I go into detail, for those of you who are not geologists, let's take a step back, and I'm going to introduce a bit about the Earth's interior. This is our planet Earth that we saw before, and you see the different layers that we have in the Earth's interior. We know this from seismology. If we have earthquake, the way the seismic wave propagate through the Earth's interior tell us a lot about the different properties, the density and so on, and we know that the Earth is layered. Our top part, we have the crust, the skin of our Earth, where we live on, And then we have the mantle, which is divided into an upper mantle, a transition zone, which extends from 410 to 660 kilometers, and the lower mantle, which go down to 2,900 kilometers. And then we have the outer core, which is liquid, made of iron-nickel alloys plus lighter elements, and the inner core, which is solid. So we go down to 6,370 kilometers. In the mantle, the minerals are silicates or some oxides. This is a zoom in of the first 1,000 kilometers. I'm not going to lecture about the mineralogy, but what is important, this is an image of what is a sample from the mantle that we have actual hand samples, and these are the main minerals. And you see they're all silicate, SiO4 or SiO6 depending. And then we have down here an oxide. Do you see any hydrogen in this formula? No, they are all nominally anhydrous. They are silicates, they do not contain hydrogen in there. We know what happens over down here because we do experiments, high pressure, high temperature laboratories, okay? But what is the take-home message here is that they do not contain water or hydrogen in their chemical formula. But actually, when we look at natural samples, we figure out that they can contain and store hydrogen in there. How do we know that? Nature suggests us so. Thankfully, we have pieces of the mantle that come up. This is a schematic of a cratonic area. So those parts that we have that are stable, very old, think about Canada, South Africa, for example. In these parts, we have the lithosphere, so the crust and the upper part of the mantle, the lithospheric mantle, they're very old, stable cratons, and they have these deep roots. And here we found this peculiar type of rocks, the kimberlites, that are explosive, rich in hydrogen and in water and CO2. They have roots deep in the mantle, and when they explode and they come to the surface, they form these beautiful diatremes, and if we zoom in, we see that they take out pieces of the mantle. They really grab them in these violent eruptions. And they give us xenoliths, or foreign rocks of the mantle, or xenocrysts, foreign crystals like diamonds, okay? And diamonds themselves, when they form in the mantle, they trap other minerals, other fluids, other inclusions, and they seal them and they bring them back with them. And when we look already in the 90s, Ross and Bell look at these xenoliths from the mantle worldwide collection. This is just a photograph, section in the polarized microscope. They realized by measuring them with FTIR that they contain hundreds of thousands of ppm water. If we look at the kimberlites themselves, these volcanic rocks, they are full of hydrous phases, so several weight percents. And if we look at diamonds, I'm going to talk about this later, the mineral inclusions actually confirm to have quite weight percent of water. So nature suggests that even though they are nominally anhydrous, they can contain water in them. So I'm going to guide you to the deep interior and show you how we can store this hydrogen in there. We start off at the top, in the upper mantle, where we have olivine. Is the most abundant mineral. 60% of our mantle is made by olivine. It's a silicate, magnesium iron silicate. The crystal structure is exemplified here. You have silica tetrahedral that are isolated. Red are the oxygens, and yellow are the magnesium or iron. So how can we put hydrogen in there? Well, we need to create some defects, okay? We need to create some vacancies, so we take out, for example, a magnesium. We create a vacancy in the octahedral site. Magnesium is 2+, it needs to be charge balanced. We can add 2 hydrogen in there, which will form hydrogen bonds with these oxygens. The same exercise, we can have it for silicon. Silicon 4+ in the tetrahedral site, we create a vacancy and we will have 4 hydrogen substituting for one silicon. And if we look spectroscopy, FTIR spectroscopy, we can look at how these molecules vibrate, these bonds, and we can quantify how much water we have in there. If we go deeper in the transition zone, olivine is no longer stable. It transforms to Wattsley, the high-pressure polymorph of olivine. This we know by experiments, and now we see that we have different arrangement. We don't have any more SiO4 tetrahedral that are isolated, but they combine. And in this, and oops, sorry, I glossed. And in this configuration, but I don't see it anymore, okay, in this configuration over here, it leads to oxygens that are underbonded. And Smith, Joe Smith, which is a professor in Colorado in the late 80s, he first, just by looking at the crystal structure, he said this, where you have the oxygens that are underbonded, could be a potential site for hydrogen. And he understood that he could host up to 3 weight% of water. Of course, you need to charge balance with magnesium vacancies. And experiments later confirmed that. And you see here an example again where you have 3 weight% of water. If we look at ringwoodite, which is stable after Wattsleyite when we start at 520 kilometers in the mantle, ringwoodite was found in meteorites as Wattsleyite before, that's why we have a name. There is another rearrangement, it's denser. We have again silicon that are isolated. We don't have underbonded oxygens like in Wattsleyite, but again Smith realized, okay, here you can store again several weight% of water. Again, you need to add some magnesium vacancies to charge balance it. And experiments confirm that you can host significant weight% of water. This is a lot. It means that the transition zone acts as a sponge. It gets all the water there. And finally, in 2014, Graham Pearson from Alberta found this not that beautiful diamond, I would say. Some diamonds are quite ugly, the ones that we study in geology. But he looked at this tiny inclusion over here, which is about 60 microns, so like your hair, more or less. And in that, they realized by doing Raman spectroscopy, another type of vibrational spectroscopy, that that sample here was ringwoodite. So it matches the one that we have from the database. This is the first terrestrial ringwoodite that we found on Earth. But what is more remarkable, they published this in Nature, of course, is that when we do the FTIR, they find out that it contains a lot of water, similar to those that were performing experiments. And they reported that that ringwoodite contained 1.4 weight% of water. If you translate that into masses of ocean, it's several masses of the ocean stored inside the transition zone. We move now to the lower mantle, and when we reach there, things get complicated. It's really challenging to do experiments at those conditions. Okay, we are around 9,000 kilometers up, even more. But we have bridgmanite. We know it's a mineral. It was found in meteorites. We have a name. But experiments, even in the early 2000s, reported contradicting results. On one hand, the school, like Professor Kepler, Natalie Wolf, and Casanova, they reported it was quite dry. You cannot store much hydrogen in there. Other people suggest, yes, there is a lot of water in there, thousands of ppm. And that is still debated today, the situation with bridgmanite. And it's still debated because we have groups that are saying, by doing measurement more accurate, the technology advances, that we have, it's quite hydrous. Others say, no, it's still dry. So the debate is still going on, and it might be going on because it's really challenging to achieve those conditions. So to summarize, what I want to show you here is again our schematic Earth with the different layers. These are the water concentrations that are observed from natural samples in ppm weight of water, from basalts, from lavas that we get, from xenoliths, those pieces that we get, the xenoliths and the ringwoodite over here. You see in the lower mantle we don't have samples. The core I didn't talk about is even more challenging. The storage capacity, you can guess how much water you have there by doing experiments. These are the predictions. So you see weight % of water in the transition zone phases. The lower mantle, maybe a desert, a dry desert, but you see there are still many question marks. And we can translate that in masses from experiment in masses of oceans equivalent, and this will be corresponding to about 3 oceans stored inside the Earth, not as liquid water, but as defects. And then to conclude this part, the question we need to ask ourselves, this finding of that ringwoodite from Brazil is representative of the whole transition zone. Can we assume that we have several oceans in there, or is it just localized? Is it like Jules Verne imagined in his journey to the center of the Earth? This is taken from Professor Kepler. And to do that, we started to look into more diamonds from different localities. In 2022, we published this paper from Padua, collaborating with the GIA, the Gemological Institute of America. We found another super deep diamond, so coming from great depths, from Botswana. So not Brazil, but Botswana, another place. And we found in this beautiful diamond, this time it was already cut, this tiny inclusion 5, where we found ringwoodite, ferropericlase, and enstatite, which was formerly bridgemanite. Finding these 3 phases together, it tells us that we are at the transition zone lower mantle boundary. So we recognize the second terrestrial ringwoodite occurrence. And also, we found that they form in hydrous environment, and we have even traces of molecular hydrogen over here. So if we keep looking, then my impression is that it's not a localized, but it might be whole, the transition zone hydrated. So to conclude, I'm gonna lead to the first question, and is where does Earth water? I hope I convince you that we have water in the Earth's interior. That is important, but now we are trying to understand, by using hydrogen in the deep Earth interior, where does Earth water come from? This is still an unsolved mystery in Earth and planetary sciences. Some people believe that water was delivered from the outer solar system, from hydrated phases like carbonaceous chondrites or comets that form beyond the snow line. And more recently, a paper by Piani et al. Proposed that actually it was already there, because enstatine chondrites that were assumed to be dry because they form close to the sun, and those are the building blocks of our planet, actually contain hydrogen, and the isotopic composition is similar to that of the Earth. So to distinguish and try to answer this question, we need to look at the hydrogen isotopic composition, the delta D, or the deuterium over hydrogen ratio of the different candidates, carbonaceous chondrites, comets, and so on, and compare it to that of the Earth, the SMO, the standard mean ocean water. This is our benchmark. But I think we're missing something here, because by comparing that to the actual ocean nowadays might not be that good, because we still don't know what was the actual original delta D of our Earth and how it evolved through time. Was it always the same, or did it change? So if we want to really answer this question, we need to know, to track how it got this water and when that happened, if that changed. I think this is not the good way to use the actual the oceans, the nowadays ocean, because as I explained, Earth is an active planet, and I think that the overage ratio has changed because of geological processes, interaction, and so on. So if we really want to do that, we need to look at deep mantle samples, reservoirs that maybe host pristine values, okay, that are unaffected by these surface processes, convection, and so on. And we need samples that are able to track this D/H ratio over time, on geological time scale, billions of years. And this is where I propose to use diamonds in my ERC starting grant, because diamonds are our best friends to track the evolution over geological times, okay? They are made of carbon, but they contain a lot of impurities, hydrogen, nitrogen, boron, and so on. And they are used to track how carbon and nitrogen behave over geological time. But we have hydrogen in there, and hydrogen has been so far overlooked. You see, we have hydrogen. We know from FTIR maps, this is a diamond. We have nitrogen and hydrogen. They are the deepest samples that we have. They reach the lower mantle, the samples that we have. They are the strongest material that we have. Once they englobe minerals in there, they are a sealed container. They act as time capsules because the oldest diamond that we have dated go back to 3.5 billion years. We have very young, some millions of years, back to 3.5. And they were widely distributed. So if we measure the D/H ratio in diamonds as a function of time, different localities, and paragenesis, we can then track how Earth evolved and the D/H ratio. Do I have some few? Okay, just to finalize, sorry. And this is what I'm going to do now with my ERC. But there is one question that we still need to answer, because we need to really make sure that that hydrogen is pristine, that once diamond forms and englobe these hydrogen impurities, it doesn't escape, and it's primordial. And that's because diamonds sit in the mantle for billions of years, so we might have some diffusion, loss, or gain, or it might quite stay there. There are contrasting results in the literature, so if hydrogen is immobile, then we are fine. It's definitely primordial. If it's mobile but is trapped by the other nitrogen that is in there forming defects, then we are also happy. If it goes around because it diffuses fast, then we are reset to the time of the kimberlite eruption, but it's still remarkable because we are going back in time. They are also very old. And so this is more the thing that we are doing with the ERC, is to try to track from the atomistic point of view the behavior of hydrogen in diamonds to see and then get an interpretation of that. So I think diamonds are our best bet to really solve this mystery. As I'm out of time, I'm gonna conclude thanking my team. Of course, I don't do this alone. I have excellent postdocs that are helping me and collaborators. And if you want to stay tuned and really know what we are doing, you can have a look at the webpage. So thank you very much for your attention. Yes.
To be sure, do I get your conclusion right that most of the Earth, water is primordial and not from?
Well, we still
primordial.
That I cannot answer yet. I'm gonna tell you once the ERC is over. I mean, we still have to do measurements for that. Well, this we need to see.
So that is still open, that question.
Yeah, that question, that's, I have 5 years project to try to solve that question.
I can show. Okay. If I understood your data on the diamond correctly, then the hydrogen was not distributed equally in your diamond, because the red was basically in a...
This one, the map?
Yeah.
Yeah.
So is there an explanation for this unequal accumulation of hydrogen?
Yes, this, I can go back.
Maybe I misunderstood the picture.
No, but this is a special image I showed you. These are some type of special diamonds, which are called asteroided diamonds.
Okay.
And in there, the hydrogen is not equally distributed.
So is there an explanation for it?
there are different growth sectors, different type of diamonds do not form all at the same time. They grow different. And you can have different sectors in them, and you can have different aggregation, for example, of the nitrogen and hydrogen, different defects. So this particular type, it's a special type. They are not like that. Yeah.
I'm afraid we have to continue as we have a time program, but I hope the chances for discussion during the break. So I would now have the pleasure to introduce the next speaker. Our next speaker is Jürgen Grötsch, who is a geologist, originally starting at the universities of Erlangen, Vienna, and at Scripps Institute of Oceanography, terminating his PhD, I think, in the late 80s in Erlangen. This was succeeded by a postdoc period in Tübingen, where he continued his work dedicated mostly to sedimentological processes and the subsurface structure. So at a much more shallower level than the one that we have just seen, exploring this part of the Earth system. He has since spent most of his professional life at Royal Dutch Shell, where at later times he even was chief geologist, and since 2018 was serving as manager for subsurface integrated workflows. In 2018, he also became president of the German Geological Society and has been a guest scientist and senior lecturer at Erlangen-University for this time period as well. And one could say, I think, from my own perspective, that Jürgen Grötsch is probably the one person in Germany that is really driving the science of natural hydrogen, so white hydrogen, and its potential for the energy transition. Based on this perspective, we will be hearing from him a talk now on the issue of natural hydrogen formation, exploration, and exploitation. Jürgen.
Yeah, thank you. Yeah, thank you very much for this very kind introduction. Yeah, it's a great pleasure and honor for me to be here to talk to you about natural hydrogen. Yeah, which is it? We first need to find our presentation. Now we have too many on here. Yeah. Yeah, so, you know, when I look on my desk at home, I have a cup of coffee standing there usually. And on the one side of this cup of coffee is actually the portrait of a famous philosopher, German philosopher, upside down. And on the other side, actually, it's his two most favorite words. And they say actually, yeah, doubt everything. And some of you may know this was Karl Marx. I think that is an important thing in science, of course. And actually, I like the German word more because it's Wissenschaft, to generate knowledge, actually. It's a bit more specific than just science. Actually, what I would like to achieve today in this talk is actually that you don't have any doubts anymore that there is a lot of hydrogen, natural hydrogen, emanating at the surface of planet Earth. So let's go into that and look at it in a bit more detail. I think you all know the challenge we are facing. Yeah, like this one here. Doesn't work. Yeah, so you know all about the challenge we are facing, and what we actually see is that the demand on energy on this planet is increasing, and also the emissions we are producing is still continuously increasing, despite many efforts we are actually undertaking. So this is not just due to the growth of population, but mainly actually due to the economic prosperity, especially in countries in Asia. So one of the things which is rather clear is that we need in the future in this energy transition more, but also cleaner energy to really fulfill that demand. And you see here like the 7 essentials on the energy transitions, and most of them you of course know. It is things like electrification, it is things like energy efficiency, it's carbon pricing, it's carbon storage, it's ending deforestation as one of our sinks on Earth, and of course it's also changing consumer mindsets and behaviors. But another 7th component is really that we need to grow new energy systems. And that's what I would like to talk to you about, and that's the story also of natural hydrogen we want to go through. But let's first look a little bit back in history, and there were many game changers in the energy systems on planet Earth, and it all started out with Prometheus in the Greek mythology giving fire to man. But in the meantime, we had wood as one of the main energy carriers. We had peat in Central Europe as a main carrier, replaced by coal, replaced by oil, replaced by gas. And now we are trying to replace it actually with other renewable energy sources. Quite a clever thing, of course, to do. And we see, and even our politicians at the moment in the limelight have recognized that the 2 main elements we deal with at the moment with respect to renewable energy, wind and solar, is not going to be enough to actually fulfill all the requirements. And that's how hydrogen came into the picture. And we have heard yesterday evening already how hydrogen can be produced. It's not a big problem to produce hydrogen, and we are producing around 90 million tons of hydrogen per year around the world. Most of it, unfortunately, is made out of fossil fuels, as you know. And if we want to have the ambition to increase our 90 million to some 400, or maybe some people want to have 500 million tons per year in 2050, we need to do something dramatically. And now that is all clear, and that's why the German government and other governments have come up with a hydrogen strategy. Interestingly enough, in this hydrogen strategy, there's no word of natural hydrogen, actually. Still, we are recognizing now that this industrial production of hydrogen is not going to work in the way we had thought. And that's due to 4 dilemmas which we are facing. And the first one is actually costs for producing green or blue hydrogen, which are way too high to make it economic and to make projects on a large scale fly around the world. The second is competition for power. Electricity is in great demand. Data centers are exponentially taking more electricity up, and therefore nobody will actually commit to get all this power needed into the system for electrolyzers. Energy efficiency is another aspect. We have seen it's not a very efficient process, and if we transport it via liquefying it, it's even terrifying how little efficient that process actually is. And then, of course, we are subject to be a victim to long-distance transport of energy nowadays already, with gas, with LNG transport, oil pipelines. And we need to get rid of actually one of these long-distance transports. And transporting hydrogen over long distances is another very uneconomic thing to do. So, what can help us in this? Wouldn't it be nice if we have natural hydrogen on this planet, actually, which could solve all of these 4 dilemmas we are in, and at the same time has a rather low carbon intensity as a whole? So that's one aspect, but there's another aspect which is tremendously important nowadays, and that is, we have focused on economic aspects of energy as one of our big components. The second aspect is the environment, of course, nowadays, the greenhouse gas emissions, and that's why we want to get away from fossil fuels. But there's a new kid on the block, and that is security. People have neglected in Europe for quite a number of decades, actually, how important energy security is. So yeah, natural hydrogen, what can be its role in this future energy system is one of the big questions. And it's interesting if you look into Wikipedia, and I hope they have changed that in the meantime, that is a statement from Q2 2023, which I always like to show my students. And that is basically what it says. And I want to convince you that this is not really the case. You need to change your mind. There's a few misconceptions around, actually. Sorry? Oh, you want me to read it? Yeah, it's written on the top here. Hydrogen does not occur naturally on Earth in large quantities. Right. That's not correct. I can. Okay, so we have many colors of hydrogen, and you have seen a little bit of a glimpse last night in the presentation very nicely already. What we want to talk really only about is our white hydrogen here, and if it actually can become a component in the future energy system. And interestingly enough, yeah, we are starting to talk about this now, but everybody knew about white hydrogen since they were little, since they turned on the television and looked at the Olympic Games, because, yeah, the Olympic flame is actually originally most likely a flame which is coming from hydrogen. And as we have learned last night, it's you can see that here in Jumeirah, south of Antalya in Turkey. It is actually, you can see the flame here. So one thing you've learned yesterday, it can't be a pure hydrogen flame. And that is indeed true. It is a mixture of hydrogen, of natural hydrogen and methane, and that's why you can see the flame in this case here. Yeah, so everybody knows about this since a long time, but interestingly enough, nobody has really looked at it. This flame is around since humans have written down records since more than 2,500 years, and it's not just one. There's 50 seeps or more, and 20 of them are burning since a very, very, very long time in history. So yeah, why didn't we really look at it in earnest a little bit earlier? And like in many of these developments in energy systems, it's actually a lot related to serendipity. A lot of these things are not very well planned, and just from my history in my career, yeah, gas in Central Europe is one of these major stories of serendipity. It was not planned, but yeah, gas took over in the 60s due to the discovery of one of the largest gas fields in the world in Europe. So in hydrogen is more or less the same. We see somebody has drilled a water well 110 meters deep, and that's why this diameter of these wells are very big. These are typical water wells, and then somebody threw a cigarette into it, and the thing exploded. And this time there was no flame, and in fact, you know, that is hydrogen of 99% purity. So yeah, it took another decade or two to actually that somebody came up and with the idea to produce that hydrogen. And in fact, that's what happened in 2012. A small company, an entrepreneur from Mali, actually made power with electricity for the village of Burakebugu. And that's the most famous place and the only place in the world which is actually producing hydrogen up to this point. We want to change that. Yeah, why do we think we can change that? There's another indication here. We know hydrogen, since a long time, is a safety hazard. It's a safety hazard in the mining industry, And one of the important examples is actually in Albania, one of the largest chromite mines in the world, which actually, based on the recent work from the group in Grenoble, is actually producing 200 tons of hydrogen per year in venting system. You know, they need to ventilate that, otherwise it generates explosions, and it has generated explosions in the shafts of the mines. So yeah, it's not the only example where the safety hazard is present. We have lots of mines around the world, and they are actually aware of these safety hazards and the production of mines. And the deepest mine in the world in Canada is about 2.2 kilometers deep. And guess what they find there? It's hydrogen bubbling out in the shafts. So we see that in many places around the world. So yeah, why didn't we see this earlier? Why didn't we recognize this earlier? And there's many reasons, and I just made a list of 12 of these, but you probably can extend that a bit further. Yeah, if you don't look for it, you will not find it. That's one of the key principles, and that's what we also see in the petroleum industry. Unconventionals is one of these stories. Nobody looked for it and nobody found it, and now the United States is the largest producer of hydrocarbons, again, due to this revolution of the unconventionals. Now, yeah, if you don't look for it, also the oil and gas industry was not really interested in that. There were much better, easier products with oil and gas, which you can produce, in fact, and also transport rather straightforwardly. And then there is no real chances to find it due to serendipity, because the oil and gas industry is working in sedimentary basins. A lot of the natural hydrogen actually we find outside of sedimentary basins. The mining industry, similarly, is working at very shallow depth, and that also is something where you don't have, you have less chances to find hydrogen. And of course, they're also not interested. They want to vent actually hydrogen rather than produce it. Lack of technology. We had gas chromatographs which used hydrogen as a carrier gas for a long time. And you can imagine, yeah, you can't measure hydrogen in such gas chromatographs. And we didn't have handheld sensors for hydrogen for a long time. We have them now, and that's why we are finding more and more of this hydrogen. And yeah, hydrogen, of course, is also very reactive. And a very last one, it was all written in a Russian language, and nobody looked at actually these publications for a long time until Skonig in 2020 all translated them. So yeah, just a few reasons why we didn't look for hydrogen actually earlier for natural hydrogen. And so the history is quite interesting, because one of the first production, or maybe the second actually I should say, production site for natural hydrogen was in Germany, 1910, in a salt mine, Leopoldshall near Stassfurt. Somebody actually saw hydrogen after Mendeleev discovered it in 1888 and produced it for 4 years at very small rates, obviously, but he produced it until the First World War broke loose and everybody forgot about it. And we are basically now, after 100 and more years, to revive that actually now and look for hydrogen in Germany. But you know, there is a history behind it, but it's not very long, and it was interrupted for more than 100 years, essentially. So where do we find it nowadays? And that's an example from Australia, from the area in Western Australia near Perth, where you have on one side, on the right-hand side, you have a craton here, and you have a sedimentary basins on the left-hand side, and you see these subcircular depressions actually there, subcircular kind of features. And for a long time, nobody really understood what that actually is, until people started to look at seismic lines, so reflection seismic across this fault. And what you see actually, you see these faults here and the interpreted fault lines, and actually these subcircular depressions are just on top of faults. And that's for us in the energy industry, of course, an indication for vertical migration paths of fluids, in this case of hydrogen. And that was one of the drivers, and nowadays we are doing a lot more on measuring it, and I just show you a few pictures on how you do that. That's actually out in the field in Germany, in northern Bavaria. That's where we recently found hydrogen. And we actually are doing that in soil gas samples. And the soil gas samples we take with these handheld sensors and pump the soil air out, and that gives us the indications for very high concentrations of hydrogen. And I always tell people, yeah, if you find hydrogen at the surface, there must be a lot more below, because there's a lot more smarter species on planet Earth than humans who are very efficient in using energy. So microbes and bacteria have used, of course, this energy source since a long time. So yeah, where does all this hydrogen actually come from? And we've heard a few examples already, but there's actually quite a plethora of possibilities of sources of natural hydrogen. And we just go through very quickly. It's serpentinization, it's iron oxidization, like banded iron formations, for example. Wherever you have iron, you can oxidize that together with water. You have radiolysis in granite, plutons. You have hydrothermal vents. You have other means of oxidizing, pyrites in black smokers. But you also have hydrocarbons, in fact. Coal and hydrocarbon basins actually are producing in a very late stage at very high temperatures, late stage of maturation, also hydrogen. You have thermal decomposition of ammonia. You can have salt. Salt has shown in a number of cases hydrogen. We have biological activities. We have faults and earthquakes which generate it. And then, thanks to Marta, we know we actually have also primordial hydrogen as one of the key sources. So at the end of, we have plenty of producers, but of course we also have plenty of consumers, and that's why we actually see rather little hydrogen at the surface. In fact, we still can measure it very nicely, but we have a lot of it, of course, already being eaten up or used by somebody else, be it geochemical reactions or be it microbes. Now, the question we always get is how much hydrogen is there? And that, of course, it took us 150 years to find it out for petroleum and hydrocarbons, in fact, to quantify that in earnest. We are here at a very early stage, but still the USGS, Jeffrey Ellis, has tried to quantify that once, and probably the best figure people kind of come up with nowadays is what are the flux rate to the atmosphere. And the number of 23 million, 24 million, or maybe a bit more is a minimum case of the expected flux rate into the atmosphere. And from that you can actually calculate how much you need to generate actually how many resources you need to generate all of this. And then he came up with another big number, which I don't want to repeat here. It's 5.6 million tons, so it's quite a large number, but that is just resources. It's not the amount of hydrogen we expect on planet Earth. It's just a figure derived from serpentinization and radiolysis, excluding primordial hydrogen. And then you can also calculate what is replenished. It's a continuous process, as you have heard already. You also replenish actually a lot of these hydrogen which is emanating to the surface. So these are big numbers, and if you put 2% of that and you compare it with the current proven natural gas resources, you could actually produce 500 million tons for 200 years. And that's basically what this paper says, but there's a lot of uncertainties around it. Still, we actually see that what we know about natural hydrogen is it is a possible renewable source in the future energy system, and we see that there's more and more and many discoveries around the world. Everywhere we find natural hydrogen actually. And I better move on before I get kicked out. So it's where we are standing at the moment is really like where the petroleum industry was 150 years back, essentially. And yeah, if you look at play-based exploration, we actually have a similar type of observations. We have sources, we have migration, we have seeps at the surface, but we also have major differences between these systems. And what we are mainly focusing is, in fact, a play concept. You see here a couple of these play concepts in the very different geological settings. What we are mainly focusing, in fact, is the last one, and that is called aquifer play. And that's what we are actually tracing in southern Germany. And yeah, just to give you a brief glimpse on that, what we are doing here, we are working in the Franconian Basin, which is this small basin here indicated by this AI-based map of geophysical data, which actually indicates the highest geothermal heat gradients in Germany next to the Rheingraben. And the area is in northern Bavaria, which is circulated here. And in all of these areas, we have found, in the meantime, natural hydrogen. And we also have looked in other areas, and we think we can also find more. Our colleagues from Fraunhofer did already find it in the Rheingraben. But we need to mature, actually, this a lot further. What we see at this point in time is we do see exploration activities, but what we don't see is the focus on exploitation, the last aspect. And that's what we are trying to do, to set up pilot production sites, the second ones after Mali, to actually test that, how much we can actually produce. So in conclusion, yeah, you've seen energy systems are driven by serendipity. Before conceptual geological models come in and play-based exploration kicks in and development concepts develop. And that's what we see also very likely in natural hydrogen. So we are at the very beginning of a development. And yeah, open questions are still there, plenty of them. Like, yeah, is there reservoirs like in natural gas? Is there sources? What are the sources, the best sources? And yeah, the question on primordial hydrogen, which has been kindly enough already explained before by Marta. And also the question on the diamonds was already explained by Marta. You can see these inclusions of abiogenic methane and hydrogen in these diamonds, and that basically poses questions which we haven't posed for many decades, which were addressed by Larin, and actually this postulation of the hydridic world he has come up with. Let me leave it at that, and I hope you are convinced that natural hydrogen is something which is worth looking into and around the globe. Thanks a lot.
Thank you very much. I was just wondering, I read recently that this primordial hydrogen, well, goes even lower to the Earth's core. There's this iron-nickel alloy, and if you measure the density is too low by 8 or 10%, and people say it's kind of with an iron-nickel alloy with interstitial hydrogen, and that there are some diffusion processes which are an eternal fuel for hydrogen in a way. Can you comment on this?
Yeah, that's correct. In fact, what we have is there is a deficiency on seismic velocities in the core of 10%. So we see a density deficiency of 10% in the core, which we can't explain if we put just iron or metals into the core of the planet Earth. So there must be lighter elements in there. And one of the theories is, of course, that we have hydrates in there, which make it lighter, and that actually the core is also, in addition to the mantle, a storage for natural hydrogen as a hydrogen source. It would, of course, be a much bigger source than anything else. Yeah, that is certainly also a possibility, that we have even more storage space in the core.
Hello. One question. When you talk about this natural gas, hydrogen gas storage sites, or this environment where it's there, I was wondering, did you observe how long they are stable? Let's say, is this something, I mean, this is a new research, of course, and if you detect one spot where you have it, did you have any experience how long you can maintain it, or how long the hydrogen is there? Because when you want to use it afterwards, of course, it is important to know that you have a stable source, right?
Yeah, yes. Yeah, we are working on the development concepts actually for natural hydrogen. So we are probably one of the first ones who are advancing that in the world. And what we are basically going after is we are using aquifers as capture areas for natural hydrogen, which are continuously replenished by ultra-basic rocks in our case in northern Bavaria. These are former aboriginal subduction zones, if you want to, which have a lot of these ultra-basic rocks with a lot of serpentinization ongoing. And that is why we believe it's continuously replenished. What we are planning to do is basically to produce it from aquifers which are collecting all the natural hydrogen which is percolating to the surface.
Yeah, I think you made a very convincing case that it is well possible that there are hydrogen deposits in geological settings. But are there any signs where you can say, yes, there is a place on Earth where there are a couple of million tons of hydrogen, and it's likely that they are actually there? Has that been detected, or is that just something that will happen, might happen in the future?
Yeah, we already know there's places where there is significant quantities of hydrogen based on old oil and gas wells which were abandoned, like in the mid-continental rift in Kansas, Nebraska in the US, or in southern Australia. So these are known areas of natural hydrogen. What we are doing is actually we are moving into greenfield areas where nobody actually has looked for oil or gas nor for hydrogen. And that is basically, yeah, we see these percolating hydrogen. It is very clear there must be very large quantities of this hydrogen. And what we think is actually that we can extract this hydrogen from aquifer sources. Now, how big these are is we are not planning to support steel manufacturers or ammonia plants. We don't expect that we can produce it in these quantities, but we think we can produce it in quantities like you need for a hydrogen gas station, fuel station, or a trucking company, or mobility services of some sort. Or other services like generating power or generating heat with it. That we think we actually we have, and we have made calculations which support that you can produce these quantities also together with other energy resources.
If I understand you right, this is about 1,000 tons per year, 1 million tons.
Yeah, these are, we are talking about production rates of 1,000, 1,500 tons per year. That's what we are aiming at, in fact. So it's basically like a windmill, a large-scale onshore windmill, the energy you can produce. The one thing, what we think is we can put thousands of them out into the world. And the replication basically makes the scale of actually what we expect to happen.
Quick, short question.
Okay. Many thanks for the talk. I have a question specifically for subduction zones, which are widely available in the Earth. I assume that this is from also like my ignorance, but I assume that the focus is the places where occur serpentinization in subduction zones. But those are deep, so I assume that also you need the pathways that could be faults or the volcanic arc. It is already known which of both are the best candidates or approaches to actually monitor which will be the best candidates to actually explore for interest place?
A very good question. We have been looking into different source areas. So we, on purpose, measured on top of granite plutones to look at radiolysis. We looked at areas where we expect predominantly serpentinization to happen, and we looked at areas with large-scale fault systems going deep down into, hopefully, the mantle. And in all areas, we found hydrogen. Similar quantities. One thing we think we do know, it's related to fault systems. So we are working, of course, along these fault systems, and predominantly thrust fault systems present in northern Bavaria are of great interest to us.
So thank you again. We're moving on to the third talk. It will be given this morning by Kevin Heng. Kevin Heng is holding since 2022 the chair of theoretical astrophysics of extrasolar planets at Ludwig's Maximilian's University in Munich. And he also holds the chief position for the university observatory there. He did his PhD in 2007 at the University of Colorado, starting his profile on researching on planetary atmospheres. This was followed up by several fellowships in Princeton and at the ETH Zurich before he moved as a professor to Bern University, also in Switzerland. He received for his research several ERC grants, a consolidator grant in the about less than a decade ago, and more recently, since last year, an ERC Synergy grant. Also, a number of awards for his research by, for example, the Royal Astronomical Society or the Academia Europaea, where he is a member of. He's considered to be one of the global leaders on the topic of exoplanetary atmospheres, and I guess this will be the topic of his presentation, called Hydrogen in the Atmospheres of Exoplanets. So, please, Kevin.
Let's see. Thank you very much for the very kind introduction. It's really an honor for me, since I'm quite new to Germany, to give this talk to such a distinguished audience. So I would like to start by asking the question, before talking about hydrogen and exoplanets, just ask the question, what are solar system planets made of? And you can approach this question like a child would. You can look at the bulk densities of our gas and ice giants, so Jupiter, Saturn, Uranus, and Neptune. And you will notice that the bulk densities are roughly on the order of 1 gram per cc. Not very different from our sun. And this is consistent with the fact that all of these bodies are made mostly of hydrogen, the theme of our symposium, with a little bit of helium. So to an accuracy that satisfies an astronomer, these bodies have roughly the same composition. Now, if you look at the terrestrial planets of the solar system, this gives a slightly different story. These bulk densities are several times that of the sun, so 4 to 6 grams per cc. And the atmospheric compositions tell a very different story. So if you look at Mars and Venus, these are dominated by carbon dioxide, but this number is deceiving because the surface pressure on Mars, which is the pressure that you will feel if you were standing on the surface of Mars, and the force per unit area of the atmosphere was weighing down on you, is roughly 1 part in 1,000 that of Earth. So in other words, Mars has a surface pressure of 1 millibar compared to Earth's 1 bar. Venus has a surface pressure of 100 times, roughly, that of Earth. So even though they have similar composition by number, they have very different atmospheric masses. Earth, on the other hand, has a very different, despite the similar gram per cc in the bulk densities. Earth has 78% nitrogen, a lot of it modulated by biology, 21% oxygen, and a sprinkling of carbon dioxide. Very different from our sun. And in fact, the Earth went through a very complicated history, and this is a cartoon that doesn't do the whole field justice. There are many people in the audience who work on very specific aspects of this big picture cartoon. It is believed that the Earth started with a nebular atmosphere inherited from the protosolar nebula that formed the sun and the planets, of hydrogen and helium mostly. And then as time evolved, Earth became a magma ocean planet with a reducing atmosphere made up of mostly hydrogen and carbon monoxide. Because hydrogen is such a light molecule, this eventually escaped the gravitational well of Earth. To oxidize the atmosphere, geochemical outgassing became important, and eventually biology also took over. So the Earth evolved from a hydrogen-helium-dominated atmosphere into a so-called mineral outgassing-dominated atmosphere. So this is all fine, and as an exoplanet scientist, I'm tempted to ask the question, does the solar system mislead us? Because I have painted you this very childlike picture that I have 3 terrestrial planets with heavy atmospheres, and I have 4 ice and gas giants with hydrogen-dominated atmospheres. But what does the exoplanet population look like? These are planets outside of the solar system. The answer will surprise you. So what are exoplanets made of is the next question. Exoplanets are planets orbiting stars outside of the solar system. The first was discovered by my Swiss colleagues in Geneva, Didier Queloz and Michel Mayor, who got the Nobel Prize in 2019, I believe. This was discovered in 1995, so this field is very young. And if you measure, astronomers have measured a whole sample of planet sizes. So what you see is planet sizes in Earth radii versus orbital period in days. And the first thing you notice is that there's no dichotomy between Earth and Neptune. So Earth is, on the vertical axis, Earth has a unit of 1, so 1 Earth radius. And Neptune has roughly 4 Earth radii. The exoplanet population doesn't have this dichotomy. There's a whole continuum of sizes in between. This is the first thing you notice. The second thing you notice is that there are plenty of planets between orbital periods of 1 and 100 days. Just to give you some reference, Mercury has an orbital period of 88 days. So most of these planets have orbital periods within the orbits of Mercury. So this picture is not too impressive, but now if you condense this 2-dimensional distribution into a 1-dimensional one, what you see is this famous, in my field, in my literature anyway, this famous bimodal double peak distribution. So this is measuring the number of planets with an orbital period of less than 100 days as a function of their sizes in Earth radii. And one of the first things you notice that's remarkable on the vertical axis is that you see this, the peak, it peaks at roughly 0.1. This means that there's roughly a 10% chance of finding one of these planets around a star. That's remarkable, because for the first time in history, this question is not philosophy. This means that if you look up at 10 stars in the sky, one of them will have an exoplanet, and if you find one, most likely they will come in multiples. In my literature, this is known as the radius valley. So there's a somewhat continuous distribution between 1 and 4 Earth radii with a little dip in the frequency at 1.8. And if you pretend that these planets have the same masses, which they do not, then the densities corresponding to these peaks, the ratio of densities is roughly 6, which means you're tempted to believe that the second peak are gaseous hydrogen-dominated things, and the first peak at 1.3 Earth radius are the rocky things. Is that true? So we will explore that. So in other words, just to bring home the point, not only are these planets extremely common, there's no analog of this in the solar system. So does the solar system mislead us? Absolutely. So when astronomers look at the actual distribution of exoplanetary systems, there's no dichotomy between Earth and Neptune. In fact, these super Earths, which are the ones to the left of the peak at 1.8 Earth radii, and sub-Neptunes, which are the ones to the right of the peak, are extremely common. 10% by conservative estimates, and some papers, if you correct for observational bias, as high as 30 to 50%. So by analogy, since the terrestrial planets have so-called secondary atmospheres, which are dominated by geochemical outgassing, and the ice and gas giants have so-called primary atmospheres, which are dominated by hydrogen and helium. Since there are planets in between these two populations, by analogy, they must be some kind of hybrid atmospheres, meaning that these planets have cores that are massive enough that some hydrogen is left, and the outgassing is being outgassed into this very old, long-lived envelope of hydrogen. So let's explore that idea. So just to send, again, this is the cartoon of what I just said. So in the solar system, you have this channel where you start out with hydrogen and helium. This is lost over billions of years. And then outgassing takes over and gives you a secondary atmosphere. In the exoplanet population, we are starting to see evidence that there are bodies that are massive enough to have a hydrogen envelope, and outgassing happens in this envelope. And of course, the natural question is, what does the chemistry of this look like? That's the basic question. Before I go there, I have to give you some basics from our field. So there's a term we use called the mean molecular weight, which I have to explain. The mean molecular weight is it's a combination of the relative abundances of different species by number, not by mass. This is a common misconception. So for example, if you have 90% hydrogen and you have helium being 10% as abundant as hydrogen, then this mean molecular weight is roughly 2.2 if you ignore all of the other heavier molecules. Because Earth is dominated by nitrogen, as I told you earlier in the talk, of 78%, the mean molecular weight is roughly 29, very close to nitrogen's mean molecular weight of 28. So now, what does a sub-Neptune's mean molecular weight look like? But first, before I show you an example, let me explain to you how this is measured. So there's a measurement technique called transmission spectroscopy, which took my community, meaning all of the astronomers, exoplanet astronomers in the world, roughly 15 years to perfect. Because in the beginning, we were just seeing essentially detector noise. And this was perfected over 3 different space telescopes, so the Hubble, the Spitzer, and now the James Webb. And the idea is very simple. The idea is not only are you measuring the shadow of the planet cast on the star, you are measuring the size of the shadow at different wavelengths. And now imagine that the atmosphere has water. So you know from the cross-section of water that there are some wavelengths where water absorbs more light and some wavelengths where water absorbs less light. So now if you measure the projected size of the planet at these different wavelengths where water absorbs more and less light, you should see a slight difference in the size, on order of 10 to 100 ppm. And this is what is being measured now quite successfully by the James Webb Space Telescope. In other words, there's a mapping between the size of the shadow and the cross-section of molecules given by quantum mechanics. So here's one example measured by the James Webb Space Telescope. This is a sub-Neptune called TOI 270d, Test Object of Interest 270d. D means that this is the 3rd planet in the system, so B, C, and D. The star is A. This planet has 1 super-Earth and 2 sub-Neptunes orbiting a rather small star. So super-Earths and sub-Neptunes in the definition I gave you earlier. This particular object has a radius of roughly 2 times that of Earth, a mass of roughly 5 times, and a bulk density of 2.7 grams per cc. So very strange. It's not 1 gram per cc, and it's not 5.5 gram per cc. Now, so when you measure the size of the shadow and you map to the cross-sections, you can figure out what molecular abundances this sub-Neptune has. And this answer is very surprising. This sub-Neptune has, by number, 2% of methane, and 2% of carbon dioxide, and 8% of water. Anyone who thinks a little bit about chemistry will instantly find this bizarre. How can methane, an extremely reduced molecule, sit alongside an extremely oxidized molecule in comparable amounts? And if you then calculate the mean molecular weight of this atmosphere, it's not 2.2 or 29. It's 5.5 with a generous error bar. So in other words, we are getting the first hints that these sub-Neptunes are a strange type of animal that do not exist in the solar system, and the influence of the atmosphere and the core are unlike anything we have seen in the solar system. So the next question to ask is, what are the birth properties of this bimodal distribution of small exoplanets? And now I should show to you a paper from one of my collaborators, Professor James Owens at Imperial College, where I've showed you this distribution of radius versus orbital period. And the idea in this paper is one models not just the observed radius, but the observed radius versus the orbital period of each exoplanet, because the idea is that the shorter your orbital period, the closer you are to the star, which means that the amount of ultraviolet radiation you are receiving is stronger, and this should allow your hydrogen to escape more easily from the planet. And one of the questions they were trying to ask is, could we match this radius valley distribution with a single underlying exoplanet population? And now before I show you the outcome, let me give you some intuition. So the answer is, sub-Neptunes are basically exoplanets where the influence of the core and the hydrogen envelope are comparable. So roughly speaking, they have equal volumes. Super-Earths, on the other hand, have cores that are not massive enough to retain their hydrogen envelopes. And now here's a quiz to see if you are listening to me. So what is the atmospheric mass of a sub-Neptune? So I've told you that, roughly speaking, the volume of the core and the volume of the atmosphere must be roughly equal in this case. And therefore, this allows you to roughly calculate what the mass of the atmosphere is versus the mass of the core. What is this value if the atmosphere is fully hydrogen? And what is this value if the atmosphere is fully water vapor? So I'll pause for 3 seconds. You can think of what you think your answer is. And now I'll show you the answer. So for hydrogen-dominated atmospheres, this is roughly 1%. So you just need 1%, the mass of the core in hydrogen, to generate the same volume as the core, but you need 50% of water to get that. And this is the answer from the paper. Ignore the blue and the red. These are just two different models, and the details between them are not so important. But the point is, you have in gray the data from the radius valley, and this study tries to match this distribution across radius and orbital period. And the answer is that this radius valley can be explained by a single underlying exoplanet population, where the rocky core is roughly 4 Earth masses, and the mass of the atmosphere over the mass of the core is roughly 2%. This is what is coming from the data. And so sub-Neptunes, basically, to summarize in this cartoon, have some kind of rocky core that is a few Earth masses, an atmosphere that is a few percent the mass of the core, and if you translate that into a surface pressure using Newton's second law, you get a partial pressure of hydrogen of roughly 10,000 bars. This is gigapascal for the geo people in the audience. And the temperature at this interface between the envelope and the core is a few thousand degrees Kelvin. We know that this core cannot possibly be inert. It must be interacting with the atmosphere. In fact, it must outgas into the hydrogen envelope. So what is the atmospheric chemistry of this object? I could give you a whole 45-minute talk on how to calculate geochemical outgassing, but since I don't have time, I'll show you the outcome. So here's one of the outcomes. So on the vertical axis is the volume mixing ratio of the atmosphere, so the relative abundance by number. On the horizontal axis is the melt or the magma temperature, that's meaning the temperature at the interface between the core and the envelope. And what is interesting is that when the melt temperature is very high, say 5,000 or so, you have a hydrogen-dominated atmosphere. And what is critical is that in a relatively short range of temperatures, from 5,000 to 3,000, the amount of hydrogen relative to the other molecules start to decrease. And so molecules such as silicon monoxide, water, carbon monoxide, silane start to become important. And this actually, just by virtue of the thermodynamics, increases the mean molecular weight as you go to lower melt temperatures. And since we expect that the radius valley has exoplanets with a distribution of melt temperatures, we expect a transition in mean molecular weight across the radius valley. So let me conclude with that. The punchline is the smaller the exoplanet, the less hydrogen-dominated its atmosphere, purely from thermodynamics. So in the direction of the orbital period, as you go to shorter and shorter orbital period, you have less and less hydrogen because the UV radiation allows the hydrogen to escape. And therefore, the envelope is less massive, and the heating due to the envelope is less, so the melt temperature is less, and this gives you a higher mean molecular weight, which I've just showed you in the last slide. In terms of the planet size, as you decrease the planet size, you have a smaller core, and therefore a smaller envelope, and therefore lower temperatures and lower surface pressures, and this again drives you in the direction of increasing mean molecular weight. And therefore, in the diagonal, across the radius valley, you expect a natural increase in the mean molecular weight, which is actually what is being measured. So I thank you for the opportunity to tell you about one line of research in this new field that we are very excited about. And to end, I will show you this new field. I'm done, last slide. So this is a new field that we just got funding for from the European Research Council for a Synergy grant. You will notice that I'm the minority partner in this collaboration. As my career goes on, I become less and less of an astrophysicist and more of a geoscientist and an atmospheric scientist. So the philosophy is that we believe we have reached the limit of how much you can understand about exoplanets purely from the perspective of a physicist. It's now time to learn the lessons from the geosciences, particularly geochemistry, and not just figure out what questions we can ask, but try to understand what questions we cannot ask that we may never get answers to. So we are trying to unify the principles of geochemistry and astronomy in a critical way and figure out what the lessons are. And I'm happy to answer your questions.
Range of planets. One would think that it's very difficult to determine very long period planets. We have several years. So could it be that there is some data missing on the right-hand side of your diagram?
Certainly there's an observational bias. So I think in the literature what people are confident about is that they can correct it out to say 100 or 200 days. So the sample is complete till then. The sample is certainly not complete till Jupiter's orbit. You can do a simple, you can do the simple math, right? I mean, the first exoplanet was discovered in 95. So we had 30 years of exoplanet research. Jupiter's orbit is 12 years. So 30 years is less than 3 orbits of Jupiter. So we do not have data to detect 3 transits of Jupiter. But we have data for the inner solar system, and we are confident that the inner solar system doesn't look like the exoplanet population.
Thank you very much for this interesting talk. I was wondering, you're looking essentially at a snapshot in time, so the ages of these exoplanets within their solar system are presumably all different during the planetary evolution. And I was wondering how that changes your picture if you allow for variations in age. May that bimodality that you pictured in the solar system as an anomaly, after all, not be an anomaly?
Well, I would say there is an observational bias towards detecting and characterizing planets around mature stars, so 1 to 10 gigayears. And simply because of the fact that you need the star to be fairly stable. You need to be able to correct for stellar flares and star spots and contamination. So that biases you towards quiet, mature stars. But luckily for us, the quiet, mature stars have ages that are consistent with that of the sun. And we do very well with stars that are like the sun, G stars. We would like to do better with so-called M stars. So these are the stars that are 10% the mass of the sun. But M stars are notorious for having a lot of flares. Their star spots are half the size of the star, and so on. So in fact, the bias works in the direction that you like, which is that we do sunlight mature stars very well. Thank you very much.
We are moving now to the last talk of this morning's session. It will be given by Klaus Blaum. Since 2007, Klaus Blaum is director at the Max Planck Institute for Nuclear Physics in Heidelberg and professor at the Department of Physics and Astronomy of Heidelberg University. He did his physics, he studied physics and did his PhD at Mainz University, followed by several postdoc positions at the Helmholtz Center, GSI in Darmstadt, the European Organization for Nuclear Research, CERN, before he went back to Mainz, developing his profile on the cooling and storage of ions, some of which we have heard yesterday, because he is also a very recently accepted member of the Leopoldina. He received a number of awards, such as the Lise Meitner Award from the European Physical Society, and also held several ERC grants. His scientific work focuses on precision experiments on ions, and as well as the development of new storage, cooling, and detection techniques. And I take it that this will also be part of the talk that he will give with a topic on Trapped for Eternity, the Cosmic and Matter Puzzle. Klaus Blaum.
I take the headphone so that I can walk a little bit around. Does it work? Okay, wonderful. Thanks a lot. Yeah, thanks a lot for the kind introduction. I'm probably the most exotic speaker of today's symposium because it will be not only on hydrogen, it will also be on anti-hydrogen. So something where you probably have heard about but never worked with. So, and of course we'll also explain what I meant with Trapped for Eternity, the cosmic antimatter puzzle. So at the beginning I will give a very broad introduction to the topic, what is matter, what is antimatter, and their properties. We'll then move on to the trapping of charged particles. How can we deal with individual particles? And Ferdi has mentioned yesterday evening that our working horse is the penning trap, the superposition of a strong magnetic field with a weak electrostatic potential. And then in the last part, I will compare the properties of matter and antimatter. That might be the proton and the antiproton, how heavy they are. That might be hydrogen and antihydrogen. The problem I'm going to talk about starts in fact, at the beginning of our universe, shortly after the Big Bang. So what you see here is kind of the evolution. So today we are 13.8 billion years after the Big Bang. And Professor Stachel has mentioned it in her introduction, but also Ferdi yesterday evening. We started with lots of energy, and then in the first couple of microseconds, the particles were formed. And everyone talked about like the proton formation, the hydrogen formation, and the helium formation. But in fact, if we believe the physics laws, if they are correct, then at the same amounts, antimatter should have been produced. So we should have not only protons, we should also have antiprotons, electrons, positrons, neutrons, antineutrons. And the question is, where are they gone? We exist only out of matter, right? So where's the antimatter? What has happened to that? It has disappeared shortly after the Big Bang, because when matter and antimatter come together, then you get a kind of a flash of light. It's mainly energy, radiation, that disappears again, but a tiny fraction has survived, and this fraction is the matter part. So what has happened to the antimatter, and where's the tiny difference? Why is there matter left and no antimatter left? So that's the problem we are interested in. A little bit of history. So antimatter was predicted almost 100 years ago in 1928 with the Dirac equation. You all know the Schrödinger equation, and you take the relativistic form of it. And then Dirac came up with his Dirac equation, and he postulated the existence of antimatter. The easy comparison I give always is that if you take a square root of 4, it has two solutions, +2 and -2. Because if you take the square of -2, you get 4. If you take the square of 2, you get also 4. And this is kind of, he also had two solutions. And one was the matter solution, and the other one, he said, this is the antimatter solution. He called it the existence of antimatter. And it took then 4 years until the discovery of the positron in a cloud chamber. So what you see here is the ionization of the gas that is in this chamber. And you see that this ionization line has the same length, it has the same thickness, but it has a different direction. So that means that the charge has been different. One has been positively charged and the other one is negatively charged. And that was clear that one has been the electron and the other must have been the positron. Another 20 years later, so 1954, 1955, Ludwig and Pauli, many people only know Pauli, but it was Ludwig a year earlier, who came up with the idea of the so-called CPT theorem, which is the charge parity time reversal symmetry. So this is a symmetry that it says that particles and antiparticles have identical properties. So if our foundation of physics is correct, with CPT is correct, then the properties of matter and antimatter should be identical. Except the sign of the charge, the size should be the same, the weight should be the same, the charge-to-mass ratio should be the same, and so on and so on. It was then 1 year later, in 1955, 1956, when the antiproton was discovered. But what is antimatter? How can we understand matter and antimatter? I like this picture here. Of course, if you have read Dan Brown's Illuminati, where a huge amount of antimatter has been stolen from CERN, Frédéric Baudry is here. He has been the head of the accelerator, the director of the accelerator division of CERN. He knows about that when that movie was also played at CERN at that time. But I can guarantee you the amount of antimatter that was stolen there took, with nowadays techniques, will take about 1 billion years to produce that amount, so there is no risk in that. Nevertheless, I will, at the very end, I come to the transportation of antimatter. What you see here is, in fact, that particle and antiparticle can be seen as two different manifestations of the same basic physical structure. That's what I would like to show here. So you would immediately say, okay, this looks like a heart. I agree, but this as well. You might say this has a certain volume, but this has the same volume. You might say this has the same shape, the same size, but this as well. But still they are different. One is a kind of the negative of the other one. What I like also is if you would bring them together, nothing is left over. It would be a flat surface. So, and that also means that protons and antiprotons, hydrogen and antihydrogen, should be the same. And in fact, the composition is a little bit different. So while the hydrogen atom is made of a proton in the nucleus, I don't go into the details what the proton is then made of, it should have the electron. And if I go to antihydrogen, then of course you have to take the antiproton as the nucleus, and you take the positron into the shell. And the reason for that is one is positively charged, the other negatively charged, that in the sum it's neutral. Production of antimatter, is it something incredibly exotic? No, it's not, because it appears naturally on Earth, namely by the decay of the proton to a neutron, a positron, which is the anti-electron, so the antiparticle of the electron, and the neutrino, like, for example, in the decay of 22 sodium to 22 neon, which emits a positron. And in fact, it gets almost daily used, namely in the application in medicine, the PET, the positron emission tomography. However, if you would like to have antiprotons, that you have to produce artificially, and at the moment, low-energy antiprotons are only produced and delivered at CERN. And here, a big thank you to you, Frédéric. He has been the one who has built up and maintained this machine to produce antiprotons for many, many, many years. So what you do is you accelerate protons to very high energies, to 99.999% or so of speed of light. And then you bombard a heavy target, it's an iridium target, and then because of Einstein's equation E equals mc squared, you have pair production, you produce protons and antiprotons, and as before with this cloud chamber, you use a strong magnetic field, and then the protons go to the left and the antiprotons go to the right, or vice versa. By that you can separate them and bring them to experiments. Let me go back to the initial problem. The matter and antimatter asymmetry. So in the Big Bang, something like 13.8 billion years ago, equal amounts of matter and antimatter should have been produced. The vast majority of particles pairs annihilated shortly afterwards, but there's still matter left. So what is the reason for that? There can be two answers. One of them is maybe there's a tiny difference in the properties of matter and antimatter, but we don't know in which properties. That might be electromagnetic properties, that might be difference in the strong force, in the composition of the proton and antiproton, might be in their weight, in the way they behave in the magnetic field, and so on. So factually, we don't know it at the moment. The other possibility is that people often come up with is maybe there's an anomalous gravitation, so that we have two galaxies. There's the matter galaxy, that's where we live in, or the matter world, that's where we live in, and there might be an antimatter world somewhere else, because gravitation might be different. Easy question, what happens if you have an anti-apple and you let it drop? Does it drop to the Earth, or would it disappear? An answer has been given recently in an experiment, the Alpha collaboration. They measured the gravitational constant for matter and antimatter, and in the error bars, it's the same and has the same sign. Anyhow, what we would see if there's an anomalous gravitation, that we have two galaxies, a matter one and the antimatter one, there should be kind of a surface in between where you would have all the time annihilations, because matter and antimatter come together and we don't see that. So my department, we are interested in to compare the mass of hydrogen, and I will explain you how we are doing that. First question, how to weigh an object? How would you do that? Well, you can take a beam balance, and you say, okay, I place my proton, my antiproton, or my hydrogen and antihydrogen on two of these sides, and then you simply look whether it goes to the left or go to the right. That's one way. The other possibility is you take a spring balance. I like that. I still use that in school here, and you get to know what the weight is. Well, none of these techniques is good, because they both require a direct contact between the object to weight, and that doesn't work. Your antiproton would immediately annihilate. So we use a method that measures the weight freely in space. And to that end, we make use of that if we ionize hydrogen, we rip off the electron, we take only the proton, it's a charged particle, and you can apply forces like the electric or magnetic force to that. And that allows us to let them float freely in space. So a strong magnetic field reveals that the ion does an oscillatory motion, because the Lorentz force equals the centrifugal force, and the particle here rotates with the so-called cyclotron frequency. Of course, you can argue, well, the particle can still escape along the magnetic field lines. That's true, but we superimpose a weak electrostatic potential, and now we have confined the particle 3D in space. In fact, the magnetic field is typically a 7 Tesla field. That's the same field strength than NMR magnets in hospitals, while here the trapping potential is only something like 10 volts difference between the end cap and the ring electrodes. We demonstrated that we have stored a single antiprotons meanwhile for 3.5 years. A single antiproton in the trap. You can look at it, you can watch it, you can measure it. That's why I said trapped for eternity. It allows us really for infinite time to trap these particles. By the way, that only works because our vacuum in our apparatus is better than 10 to the minus 19 millibar. That's 24 orders of magnitude lower particles in the 1 cubic centimeter volume as we would have here in this room. That's how our panning grab looks like. In fact, it's a stack of panning grabs. There are 5 on top of each other, so that we can do different measurement schemes. The most important quantity, and that's the only equation I'm going to use today, is that the number of revolutions, omega, where is it here? Omega, that's the number of turns the particle does in the magnetic field per second, is given by its charge, it's given by the magnetic field strength, divided by the mass. And that's very easy now. If I'm interested in the mass of the particle, I just have to count the number of turns. I can neglect the charge, but I have to know the magnetic field. The magnetic field needs to be calibrated, and Ferdi Schütt yesterday said that his favorite element is hydrogen. In fact, Ferdi mine is carbon, because I have to use carbon as the reference mass to calibrate a magnetic field. We always weigh particles against 12 carbon, because the unified atomic mass unit is defined as 1/12 of the mass of carbon-12. Okay, so now I know how to store the particle, but how can I measure the number of turns? How do I know that the particle, in fact, our particle does 30 million turns per second, and you count them for minutes, for hours, for days. And the way to do so, and you have to do it non-destructively. So it's not like that you can impinge the particle on a detector and you said, okay, now I have the particle. You have to do it non-destructively. And we are doing it via the so-called image current detection technique. So a revolving charge here induces a tiny, tiny current here in the segments of the ring electrodes. It's really very tiny. It's 10 to the minus 15 ampere. That's 16 orders of magnitude lower than the current you get from your power plug. And then you do the Fourier transformation. So this is the signal that you then get. And that from this oscillation, and you do the Fourier transformation. And then from this Fourier transformation, you get the frequency. As said, 30 million revolutions per second. The oscillation amplitude of the particle is something like a couple of nanometers. So that requires very sophisticated detection techniques. In fact, if I compare it, if you would be here on Earth, and there would be a person on the Mars that lightens a lighter, you would be able to see it with your bare eye. That's the sensitivity that we have to detect the induced image current of a single particle, a single proton in a penning trap. First question, how heavy are the building blocks of matter? So how heavy is a proton? How heavy is an electron? And with that, how heavy is a hydrogen atom? We did world record measurements on that, exactly using this balance of an ion penning trap. And Ferdi Schütt gave this number already yesterday evening. It's a 13-digit number. We improved the previous best value by a factor of 3. In fact, the president was sitting in the first row, Professor Haug. He turned around and said, Klaus, you must be a nerd. I took it as a compliment. But in fact, if he would have seen this number here, he probably would have called me a super nerd, because if you look at the number for the electron mass, it's a 15-digit number. It's a bit of cheating, because we are allowed, if you give it in atomic mass units, you are allowed to add a series of zeros here. So in fact, it's also a 1 times 10 to the minus 11 measurement. And if you plug them together, knowing that the electron is bound with 13.6 electron volts, you get that as the mass of the hydrogen atom. Unfortunately, we are not in the Guinness Book of Records, but we are in the CODATA mass table. So if you look it up, this value is 100% given by my department. So at the moment, we keep the world record on the proton mass, on the electron mass, in fact, even on the neutron mass. How does that compare? Ferdi Schütt gave yesterday evening the example of that. The precision that we have measured here is the precision of that you can weigh an Airbus or a Jumbo 737, and you know where an ant is there as a blind passenger. In fact, we improved that meanwhile by more than an order of magnitude. So if we go down now, if you take the Eiffel Tower, which has a weight of 7,300 tons, in fact, we are now able even to measure where an ant is climbing up the Eiffel Tower. Our next goal is that we might even be able to measure at what altitude the ant is climbing because of the gravitational redshift, but we will see whether we are able to measure that. Anyhow, that's the precision on an atomic scale. We wanted to do the same with the antiproton or the antihydrogen to see whether they weigh the same. We have set up to that end BASE. It's an acronym for Baryon-Antibaryon Symmetry Experiment at CERN. At the moment, the world only place that provides low-energy antiprotons. You see here the superconducting magnet. You see the cryogenics. Everything takes place at 4 Kelvin, at minus 269 degrees centigrade. Lots of complicated electronics. What does it take to operate? What does it take to operate such a machine? Well, we have one project leader. We have 2 postdocs, 4 PhD students, 2 master students. So typically 6 to 8 people. The costs are about 3 million euros to build up such an apparatus. The setup time was incredibly fast because we have a twin experiment in Heidelberg, so we just duplicated it, transported it to CERN, so it took only 2 to 3 years. The runtime is about 10 to 15 years, and then it's simply outdated because you need higher stability in magnetic fields and so on. So what is the result? You store a proton, you store an antiproton, you let them oscillate. Of course, because of the different charge, one turns to the left, the other turns to the right. And you compare the frequencies. You compare them for a second, for a minute, for a day. According to our CPT theory, of course, the number of revolutions should be the same because the charge-to-mass ratio has to be identical. That's our understanding of quantum field theory. If we would find a difference, that would be really amazing. Let's say it like that. Okay, so the ratio of the revolution frequencies corresponds to the ratio of the masses. It's simply this equation of omega c, cyclotron frequency, and if you compare the frequencies, the charge cancels out, and you take then the ratio of the masses. Standard model of particle physics says particles and antiparticles are identical. Let's see what our result is. That's how the penning trap looks like. Mass of the proton divided by the mass of the antiproton. And our latest result is 1.0000000000003 with a 16 uncertainty on the last digit, in perfect agreement with unity. This is the world best measurement, the world best test of charge parity time reversal symmetry on the baryonic sector, published 3 years ago and 2 years ago. And in fact, now you can also, since we have also measured the electron and the positron mass, knowing the binding energy, you can express it now also the mass of antihydrogen. And you see the amazing agreement. It's up to the 11th digit, and that's only here 892, and you have 889, but with an uncertainty of 37, so in perfect agreement. The matter-antimatter problem has not yet been solved. There's another quantity that we are interested in. So you cannot say, okay, this is strong force. The composition of the proton, the mass of the proton might be strong force. What about electromagnetic force? So the electromagnetic force defines the energy with which the electron is bound to the proton in hydrogen. Maybe we can check that. So you see here now, this is the level scheme. You have the ground state, you have the first excited state. That's what we call the Lyman alpha transition. It's the 1s2s transition at the frequency of 243 nanometers. And that energy difference, or that wavelength, has been measured with incredible precision. It's in fact the best physics quantity that has ever been measured. No surprise that I go first. Oh no, let me once more go back. So there's a second quantity, namely here the ground state hyperfine splitting, that has also been measured with 12 digits. And by the way, the transitions here that gives you to the second state gives you the Balmer series. So if you have the hydrogen emission spectrum, that's the one here. If you have the absorption spectrum here, and we are interested in whether these spectra look identical for hydrogen and antihydrogen by measuring here the energy differences between the ground and first excited state, for example. This 1s2s transition, as mentioned before, is the physics quantity with highest precision. It's a 15-digit number. You see it here. And in fact, it has been measured by our Nobel Prize winner Ted Hensch a couple of years ago. He got the Nobel Prize in 2005 there were 3 people, Hall was also involved in that, for their contribution to the development of laser-based precision spectroscopy. It's precision measurement of the energy difference between the ground and the first excited state, the 1s2s transition. That's rather complicated. You can also calculate it to incredibly high precision, and you compare theory with experiment. What you have to do is you have to calculate, of course, Bohr, Schrödinger, Dirac, but then you have to take into account that the proton has a certain volume. It's not a point-like nucleus, so it has a certain extension, and you have to calculate the influence of the extension of the proton to the electron. You have to correct the relativistic recoil and so on. Already this looks complicated, but there's much more that you have to do. These are all terms that have been calculated to the 15-digit number to get the comparison between the 1s2s experimental value and the theory value. We want to do the same with antihydrogen, and it has been done by the so-called alpha collaboration. And the question is the energy difference the same? As said, this is now electromagnetic force. It's the binding of the electron to the proton or the binding of the positron to the antiproton. And yes, it's the group of Jeff Hengst, you see here the antimatter factory AD at CERN, who has done this experiment a couple of years ago. You see here the resonance transition, 1s2s, at that time measured to the 12th digit, 10 to the minus 12, while in the hydrogen system it's still 10 to the minus 15. That's mainly because of the quantity that you can produce. It's a statistical effect. You can produce and do more statistics on hydrogen than on antihydrogen. But also here, there's a perfect agreement with the hydrogen value. Still no disagreement. That means we have to look further. The main limitation at the moment from this experiment is coming from the harsh environment of CERN. So CERN, Frédéric Baudry, likes to ramp up the magnets up and down almost on a second scale because of the Large Hadron Collider that cause disturbances and so on. The experiment in my lab in Heidelberg have been done in a laboratory where we have a temperature stability of 10 millikelvin per day. It's a room 4 times 4 times 4 meters. It's 100th of a degree per day temperature stability. Impossible in an accelerator hall like the AD, where you have typically maybe 2 degrees. That's a factor of 100 worse. So the idea was born, well, why not to transport the antiprotons and the antihydrogen to the places where you can do the best measurements? For example, the German Metrology Institute in Braunschweig. But you have then to develop a tool that allows you to transport the antiprotons and the antihydrogen. That was a project by the ERC group leader, Christian Smora. He came up with the idea to build base step. It's an antimatter transport. And you see here in the inside, there's a penning crab. You need all the electronics and so on to store it. And in fact, just a couple of weeks ago, we succeeded with about 1,000 protons. So this is the AD hall. It's a hall of something like 40 meters times 100 meters. The protons were captured here in the penning crab, then lifted with a roof lifter, transported out. And you see that's the CERN area. That's about 4 kilometers in circumference. And we transported the protons, 1,000 protons. In fact, 4 kilometers, it took us 4 hours. So that's 1 kilometer per hour. It's not the highest speed. But it was only for a demonstration. And we succeeded to do so. We brought back the protons. We could do experiments with that. And when we are going to do that with antiprotons, there was a press release by the Business Today called World's Most Expensive, I'm not so sure about that, and Most Dangerous matter about to take a road trip for the first time. Should you be concerned? Okay, the answer is you should not be concerned. In fact, what I told the people that are responsible for the radius safety is, even if you have 1,000 antiprotons and they annihilate within a second or so, the radioactivity produced is less than when you carry a banana in your pocket. But I didn't like that comparison, to be honest. So anyhow, I'm at the end. I would like to acknowledge my team here. It's more than the antimatter team, but these are the people doing high-precision penning crab spectroscopy at the MPIK in Heidelberg, a wonderful team. And with that, I'm at the end, and thanks a lot for your attention. Thank you.
Thank you, Klaus. Wonderful. What are the practical steps you have taken to increase the precision of what you do? What gets you there?
Very, very good question. It starts with, first of all, in the past, maybe 20 years ago, before I entered the field, people already did this measurement of the number of revolutions. But what we introduced was that we no longer count the number of turns, we were able to resolve the phase. So in fact, instead of saying the particle does 20 million turns per second, we are able to say it does 20 million turns in 3 degrees or 5 degrees. By that, you gain a factor of 100. So we have a phase resolution of 3 degrees out of 360 degrees. That immediately boosted the field by a factor of 100. So we developed techniques where we can even have a phase resolved measurement of the revolution frequency. That was probably the biggest step. Then we have developed new tools for magnetic field stabilization systems. So our magnetic field is now stable down to 10 to the minus 12 per hour. In the past, it was typically 10 to the minus 9. Very sophisticated techniques. You take shim coils that give an intrinsic stability and so on. So a lot of it is technology-driven. We changed the power supplies. Typically, you had standard power supplies with a stability of something like 10 to the minus 6 volts or so per hour. We went on to use now the Josephson junction effect. We use JJs as power supplies. They are stable to 10 to the minus 10. So every single device in the apparatus has been completely changed to most modern techniques based on quantum effects.
Yeah, Klaus, first a little fact that will amuse you. For the ALICE TPC at CERN, we have a volume of 100 cubic meter at better than 100 millikelvin. So it can be done also over big volumes if you work hard. Now, my question is, when you showed these 2 traps to measure the proton and antiproton mass, I was wondering what is more challenging, 2 setups and the difference between these setups, or the time difference if you would put the same part?
The problem is that a trapping potential for a proton, it looks like that. So you have 10 volts, you have ground potential, so you get a potential like that. Unfortunately for the antiproton, you would have to invert that. Because in the trapping potential that traps a proton does not trap an antiproton. You have to invert the polarity. To invert the polarity and to reach 10 to the minus 12 means you have 10 volts that needs to be accurate to something like a couple of femtovolts. That's impossible to do. So in fact, what we did, we took a proxy we took the antiproton and the H minus ion. Oh, is it? Okay. We took the antiproton, which is negatively charged, and as a comparison, we took the H minus ion. So this is a proton with 2 electrons attached to it. But since we have measured before the electron masses, and since the binding of the energy of the electrons is known, you can compare these two species. And then you can use the same trapping potential, because both are negatively charged. So that was a tiny physics trick that we have to apply to get the same charge, and to use the H minus ion versus the antiproton. Yeah, right, and Johanna, thanks.
Klaus, excuse my naive question, as a non-expert. So when you are talking about this matter-antimatter situation, in the very beginning of the Big Bang, you have huge energy release. So in such a situation, isn't it feasible that you have a kind of a symmetry break by fluctuation, and then self-amplification of one class and suppression of the other class? Meaning when you have a huge control that's many times,
Indeed, these are part of the solutions. There is a similar comparison, that is, people are looking for so-called non-constant fundamental constant, like if the fine structure constant alpha is constant. It might be constant today, but it might also be probably that it has not been constant. And it's the same there. At that time, you might have maybe things like that, like spontaneous symmetry breaking or so. So these are theoretical ideas that are going to be developed. And I should also mention that I was talking about high precision experiment at lowest energies, but similar questions get addressed, for example, by Johanna here, where you try to do high energy physics experiments at lower precision, but exactly to go into that direction, so that you go towards more higher energies and see if you see effects like that there. And I wouldn't call that, yeah, these are complementary experiments. So you're absolutely right.
Thank you, Klaus, and congratulations for all this measurement. Amazing, and all the technology you have to do that. I was expecting you will give any news about this behavior of matter, antimatter, and in gravity.
Yeah, mainly I was running out of time, but you're absolutely right. So what has happened is that after after antihydrogen has produced, you can you let it fly, and then you look whether the neutral antihydrogen is going up or is going down, like a kind of interference spectrometer, and it was shown that it falls like matter down to Earth. So the G, the gravitation constant G, 9.81, is 9.84 with an uncertainty of 20 on the last digit, also for antimatter, for antihydrogen. So also there, the precision is by far not that reached what has been reached here in this field. It's mainly because you deal with neutral matter, but it is clear that the sign of the gravitation constant is identical for matter and antimatter. That was a big experiment.
Of course, one can only congratulate to truly wonderful experiments that you are doing. I should comment that at the Leopoldina a number of years ago, there was an experiment discussed, a hypothetical experiment, on chiral antimatter systems, where you could reach, in principle, a relative accuracy of 10 to the minus 30. But of course, that's not something to be done in the near future. But in principle, such an experiment is conceivable.
So your idea is to produce molecules that have different chirality?
In principle, one can have hydrogen.
Okay.
Of course, the only thing you can
We are maybe not that far away. Our next proposed experiment is to do spectroscopy on H2 bar minus.
Yes.
Which is the anti-hydrogen molecule. That's exactly what we are working right now. We have written a proposal on that. So one idea is to measure deuterium, anti-deuterium. That's probably easier to get. And the next proposal is exactly to do molecular spectroscopy. I mean, you won't have a chiral molecule, but at least you have H2 bar minus for the
in principle, a large hydrogen cluster, this is a possibility, could be chiral, right? And you could, in principle, make antimatter. Of course, if you could do CHFClBr or another chiral molecule in antimatter, that would be even better, but that is very difficult. But hydrogen clusters, in principle, are conceivable.
Are you a theoretician? No, the reason why I'm asking is the production of of anti-hydrogen as an atom is something like 10 per hour. To produce the anti-molecular hydrogen is about 1 per week. What you are proposing is probably once in my lifetime or so. Yeah. That's true. That's true, but I like the idea, yes. Thanks a lot.